Today's lesson is on the topic of significant digits. We're going to talk about the rules and how to perform calculations involving significant digits. So our learning targets are to be able to explain the rules for counting significant digits and to determine the number of significant digits to record when performing calculations. So there are two types of numbers, exact and approximate or measured. So for exact numbers, some examples are if you are buying a dozen eggs at the grocery store, you're going to buy exactly 12 eggs, not 12 and a half eggs or 12.2 eggs, but exactly 12 eggs. If you're evaluating time and you're looking at the number of seconds in 1 minute, it's exactly 60 seconds that we have in 1 minute, not 60.32 seconds per minute, but exactly 60. Approximate or measured numbers involve measurement. So like you are measuring the length or the width or the speed or the mass or the volume. And for that, you would need to determine the number of significant digits based on the precision of your measuring tool. Let's talk a little bit more about measured values before we focus on the rules of significant digits and calculations involving them. So how do we deal with measured numbers? We use significant digits and figures. So just understand that if you hear the phrase significant digits or significant figures, they are used interchangeably and they mean the same thing. Now, if you are measuring your weight on a scale and the scale reads 125 pounds, that doesn't just mean that you weigh 125 pounds. It may be that you actually weigh 125.325462, etc. Okay, pounds. So this value here on your scale means that the precision of your scale goes to the ones place. Okay, my scale at home happens to go to the tenths place. So if I step on my scale at home, it might say 112.8 pounds. That doesn't mean I'm exactly 112.8 pounds. I could be 112.8532746, whatever pounds. The measurement that is recorded depends on how precise my measuring tool is, my measuring tool being my balance in this case. So the value that is recorded is based on the precision of the measurement tool. Only the final digit recorded is an estimate. So when you have a digital scale or digital equipment, you can just record whatever shows up on the screen. However, if you're dealing with a measuring tool such as a triple beam balance or a graduated cylinder, then those instruments have lines of calibration. So you would have to record your last digit as a guess or as an estimate. So let's look at the rules for counting significant figures. First, we'll look at the overall rules. So number one, all non-zero integers, 1, 2, 3, 4, 5, 6, 7, 8, 9, those are all considered significant. Number two, zeros. Leading zeros are never significant. Captured zeros are always significant. Trailing zeros are sometimes significant. So we're going to talk about each of these three types of zeros in greater detail. And then finally, exact numbers. And we talked about what exact numbers were. So, and we'll get to that as well. So let's look at the first rule again. Non-zero integers always count as significant figures. So for example, if we have a number 4,567, because these are all non-zero integers, all four of them are considered to be significant. Now let's look at zeros. So there are three types of zeros, if you recall. The first type of zero we call leading zeros. Leading zeros are never counted as significant figures. So what do I mean by leading zeros? Leading zeros are zeros at the beginning of a number. So for example, 0.0486. These two zeros right here are considered leading zeros because they are at the beginning of the value. So these two zeros would not be considered significant because leading zeros are never counted as significant. So this value would only have 3 significant digits. The next type of zero we call captured zeros. Captured zeros are always counted as significant. So what does the captured zero look like? 160.04 has two captured zeros right here. So these two, because they are caught in the middle between two non-zero integers, we call them captured zeros. These two are always counted as significant figures. So we would say 160.04 has 5 significant digits. The next type of zero is called trailing zero. So trailing zeros are the opposite of leading zeros in that they are trailing behind. They're going to be at the end of the value. This is conditional. Trailing zeros are only significant in the presence of a decimal. So let's look at an example. 9.300. Both of these are considered trailing zeros because they are at the end of the value. And because there is a decimal present, they are both considered significant. So this value will have 4 significant digits. Take a look at 0.0080. We have 2 types of zeros here. Can you determine how many significant figures are in this value? So up front, 0.00, we're starting off with leading zeros. And remember, that was the first rule on the zero topic. Leading zeros are never significant. But here we have a trailing zero. And trailing zeros are only significant when we have a decimal. And sure enough, there is a decimal there. So in this value, we only have 2 significant digits, the 8 and the 0. Let's move on to exact numbers. So exact numbers have an infinite number of significant digits. All counting integers are significant figures. So let's look at a few more examples. 1 inch equals 2.54 centimeters exactly. Not 2.546382. No, it's 2.54 centimeters exactly. So all 3 of those are significant. 1 liter equals 1,000 milliliters exactly. So this entire value, 1,000, the 1 and the 3 zeros are considered significant. And then finally, we have 14 marbles in the box. So this is if you have a set number of objects in front of you, and in this example, it says 14. Both of those numbers are considered significant because they are exact numbers. You don't have 14.2 marbles or 14.6 marbles. You have exactly 14 marbles in the box. Now, if the rules are challenging to remember and apply, there's another technique that you can use to understand how many significant digits are in a value. So it requires a little bit of creative thought. So if you notice here, this is the map of the United States. And on either side of the United States, we have 2 major bodies of water. On the left, we have the Pacific Ocean, and on the right, we have the Atlantic Ocean. Okay, so on the left, the P, for our purposes, actually stands for point. There is a point present, a decimal point present in your value. The A will stand for, not Atlantic, but absent. So the decimal point is absent. It is not there. So now let's take a look at how to apply this analogy. So given this value, 0.000008, let's evaluate how many significant digits there are. The way you would apply this is you would look to see if your value has a decimal point, and it does. Okay, it's right there. So if your value has a decimal point, you begin counting from the Pacific side or the left side. You begin counting significant digits in this direction. And the only rule is you begin counting at the first non-zero number you encounter. So our first non-zero number happens to be 8. And once you keep counting, you count till the end. Well, we've reached the end. This is it. So this means that we have 1 significant digit in this value. 1 significant digit. That's it. Let's look at another example. In this example, we have no decimal point. So the decimal point is absent. That means we're going to start counting from the Atlantic side. Now, the only rule is you begin counting from the first non-zero number. And once you start counting, you count till the end. So our first non-zero number is 7 when we're counting from the Atlantic side or from the right side. Once you start counting, you count till the end. So 7, 0, 0, 4, and 1. These are all significant digits. So that's a total of 5 significant digits in this value. Let's look at the next problem, 20.0. This time we have a decimal point, so we'll begin counting from the Pacific side. You start counting at the first non-zero number, which is 2. And once you start counting, you count till the end. So that is a total of 3 significant digits. Just a couple more. 0.0190000230. This also has a point. So we're going to begin counting from the Pacific side or from the left, and we're going to start with the first non-zero number, which happens to be 1. Once you start counting, you count till the end. So 1, 2, 3, 4, 5, 6, 7, 8. So that's 8 significant digits in this value. Next, 10 million. 10 million has no decimal point. So the decimal point is absent. We will begin counting from the Atlantic side or from the right side. And you start counting at the first non-zero number. Well, the first non-zero number is 1. And that's it. We've reached the end. So that is 1 significant digit in this value. And our last example is expressed in scientific notation. This value has a decimal point, so we will count from the Pacific side. And we'll start with the first non-zero number, which is 5. Once you start counting, you count till the end. We have reached the end, 5.80. That is 3 significant digits. When you are evaluating a number in scientific notation, you can disregard the base of 10 with the exponent in counting your significant digits. Focus on 5.80, the number that precedes the base of 10 and the exponent. This slide shows you how to evaluate each digit in a number. So notice the numbers, the zeros at the beginning. These are all leading zeros. And remember, leading zeros are never significant. They're only used as placeholders to preserve the value of the digit that follows. 4, the next digit, is a non-zero integer. Remember, non-zero integers are going to be significant. The zeros in the middle are captured zeros. So these captured zeros are always significant. Next, we have 4 and 5. These are also non-zero integers. So for the same reason as this 4, they are going to be significant. And then finally, we have trailing zeros. So these trailing zeros, because there is a decimal present, they are significant. Now let's look at the rules for counting significant digits in mathematical operations. We'll start with some addition and subtraction. So the rule for addition and subtraction is to use the value in your problem with the least number of decimal places to determine the number of significant figures in the sum or difference. So let's look at an example. 6.8 plus 11.9342 grams. 6.8 stops at the tenths place. 11.9342 stops at the 10,000ths place. The tenths place is the least precise value. This is the least precise value present. So if these are measurements, and they are because you can see the grams label on both of them, your final answer can only be as precise as your least precise value. So the rules of significant digits for addition and subtraction are that you must round your final answer so that it matches the value that is least precise. So even though our calculator answer comes out to 18.7342 when we add these values together, we need to round our answer to the tenths place. This is where we will stop because our initial value, one of them stops at the tenths place, and that's the least precise value. So our final answer then is 18.7. You don't round the 7 up because the number that follows the 7 is a 3. And according to the rules of rounding, you keep the value in the tenths place the same because the number that follows is less than 5. So 18.7 grams is our final answer there. Next, let's look at another example. So here we have 2.45 centimeters plus 1.2 centimeters equals 3.65 centimeters. This is our calculator answer, not our final answer. Okay, if you look at the first value, 2.45 centimeters, that stops at the hundredths place, and then 1.2 stops at the tenths place. So I've highlighted 1.2 in blue to indicate to you that that is the least precise value, and that is what our final answer will be based upon. So even though 3.65 is our calculator answer, we're going to round our final answer to the tenths place. So our final answer, because of the 5, we're going to round the 6 up to a 7. So our final answer is 3.7 centimeters. Let's look at another example. Here we have 7.432 grams minus 2 grams equals 5.432 grams. So this is our calculator answer, not our final answer. Let's look at our values. Our first value goes to the thousandths place. This 2 at the end of the value here is in the thousandths place. And then the 2 that we're subtracting by only goes to the ones place. So the value highlighted in blue is our least precise value, stopping at the ones place. So our final answer must also stop at the ones place. So we're going to round 5.432 grams to just 5 grams. And that is our final answer. Now let's look at the rules for multiplication and division. For multiplication and division, you're going to use the least precise value to determine the number of significant digits in the answer. So you're going to count the number of significant digits in each value being multiplied or divided, and then limit the significant digits in the answer to the lowest count. So let's look at an example. 6.338. So evaluate the entire number. 6.38 has 3 significant digits. These are all non-zero integers. Okay. 2.0. That has 2 significant digits. The 0 here, this is a trailing 0. So trailing zeros are significant in the presence of a decimal. So our calculator answer is 12.76. But according to the rules of significant digits, your final answer when multiplying or dividing needs to be recorded to the lowest number of significant digits. So 2 is our lowest number of digits. So our final answer will also be recorded to 2 significant digits. So 12.76 will be rounded to 13. Let's look at 2 more examples. So in our first example, 56.78 times 2.45 centimeters equals 139.111 centimeters squared. So our first value, 56.78, has 4 significant digits. Our second value, 2.45, has 3 significant digits. So because 3 is the lower number of significant digits, our final answer must also be rounded to 3 significant digits. So 139.111 will simply be rounded to 139 centimeters squared. Final example, we're dividing 75.8 grams divided by 9.6 milliliters. So our first value has 3 significant digits, 75.8, all non-zero integers, 9.6, also non-zero integers, 2 significant digits. Even though this is our calculator answer, we can't keep it all, okay? So 2 significant digits is what we have to round to. So 7.8958333, we're going to round that to 7.9 for 2 significant digits in our final answer. And then don't forget the label, grams per milliliter. And that's it for the rules of significant digits and calculations.